Action!
Alright, this is a video on polar coordinates. I'm actually going to go ahead and get rid of the cute pig face. Alright, I'm Josh, and the first thing you need to know...
And I'm Robin.
There's Robin. Hi, Robin. The first thing you need to know about polar coordinates is that they are measured with r and theta. R would equal the distance, and theta would equal the angle, or represents the angle. So Robin's going to go ahead and quick show you something for those two.
Oh! Alright, so
You're just having
R being the distance,
I think that's your head,
is going to be the distance from the center. So if, we're out here, then our R is 5, because 1, 2, 3, 4, 5. So, that radius can go in any direction. That's why we have this graph here drawn, shows the radius. And then it also shows the theta, or the angle, which is the angle from this line here. So as we go up this way, we get towards 90 or pi over 2. And then we keep going, and this is 180, not 0. Even though it might seem like it's 0 because it's flat, it's 180 because we measure from this side. So now let's talk about some polar functions.
Right.
I want a hat first. Gas mask.
Alright. Very nice. Oh, I don't want a gas mask. Oh, shoot.
Get
rid of the gas mask. Oh, okay. I don't want to get eaten. Alright. Okay, the next thing is that R equals... Oh, good. My eyes are on fire. The next thing is that R equals F theta is the general formula for polar coordinate equations. Now, we're going to go ahead and give you... Oh, goodness gracious. A quick example. Robin's going to show you how to graph and then find the area of R equals 4. I'm going to actually go ahead and write that up here so you remember exactly what we are measuring. We're measuring R equals...
And by measure, he does mean graph.
Right.
Alright, so now pay attention to the back screen. Ignore Josh. I want him to give me a fancy hat.
Okay, well, first I got to erase the R equals 4.
Alright, so R equals 4, what we're going to do is go out to R equals 4, which is 1, 2, ooh, policeman. I like
you got to be shorter for
3,
this. The policeman hat, you got to be shorter.
4,
there you go.
Yeah. And now we're going to graph, it's just a circle, because no matter what the theta is, or the angle, the radius is always going to be 4.
That's the tiniest police hat I've ever seen.
Something funny to say that I'll say after the camera's done rolling.
Circle, 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 circle.
Voila. So now what I'm going to do is I'm going to show us how to take the area of this bad boy. So we know the radius is 4, so if we were to use our conventional circle, area finding method, we'd say pi equals r squared, pi equals 16 pi. So now let's find it the calculus way, which is slightly more exciting and more difficult because it's just a circle. So let's go. The general formula for an integral of a circle, I'm going to write over here as Josh zooms in for me.
Of course I'm going to zoom in.
Is the integral
find the zoom in button.
From A to B
Zoom
over
in.
r squared
Look over there.
over 2 d theta.
Make sure that that's the center.
So there is
Go
our
and
general
fix the
formula for this. Josh is going to fix the light so things start showing up better. While he's doing that, I'm going to get started writing the area out for this specific function. So we have integral from 0 to 2 pi. Because this circle, as we can tell, goes all the way from here all the way up and around.
You can see it better.
So it ends at 360. That's where we're integrating from. So we're integrating from 0 to 2 pi.
Moonlights are enough.
And the radius is going to be 4, but we have to square it. So it's 16 over 2 d theta. So we go from, that's 8. So we're going to integrate it, 8 theta from 0 to 2 pi. And we have 16 pi minus 0, 16 pi. Crazy? It's exactly what we got with the conventional formula for a circle. You see that police hat popping over my eyes. Oh yeah. So now Josh is going to give us another more interesting problem.
Fix my zoom because I look all... Oh! Shoot, there I am. Actually, I'm not going to give it to you. I'm going to find somebody fun to talk to. It's going to be...
Statue of Liberty.
The Statue of Liberty is going to explain this one to you. Alright, the Statue of Liberty is saying that we are now going to...
BAM!
Oh, goodness gracious. We are now going to be taking the area between r equals 4 and r equals 4 sine theta. In order to do this, Robin is going to go ahead and show you a neat formula and some... Oh, actually, you know what? We have it pre-written for you. Let me get rid of the Statue of Liberty so that you can view what we're doing here. Alright, Robin, can you explain that?
In the interest of saving time and some very ugly drawings on this cramped whiteboard we've got going, I've already drawn out the integral. So what we have here
Having a bad day.
is this fancy integral for the area between the functions that I'm going to draw. The functions are r equals 4 and r equals 4 sine theta. Here we already have our r equals 4. Now let me draw the 4 sine theta. So what we're looking for is the area that's inside r equals 4 but not 4 sine theta. So we're looking for all of this area.
In case you can't see what he's scribbling there, it's a little bit hard to see. It's outside of this smaller circle.
So our strategy here is going to take the area of the bigger circle and then subtract from that the area of the smaller circle. So here, this column over here is the area of the larger circle, which we already showed on the whiteboard. This over here is the area of the smaller circle. Note the difference in the parameters of integration. Whereas this one went all the way from 0 to 2 pi, this one only goes from 0 to pi, because that's where the theta here, where it gets to 0 again, is at pi, not 2 pi.
Correct.
So we plug it in. Here we had to use a fancy double angle identity, and basically we took sine squared and turned it into cosine squared minus 1 over 2, and then continued integrating. Here we plug them in. Voila, that turns into a 2/0. That's pen writing for you. And then at the end we get 12 pi.
That is a 12.
That is a 12.
Normally 12s would look a little bit more...
He's going to draw you a more perfect 12. And then we're going to play with his editing program for just a few minutes. We have to get our friend over here.
Woo! 12!
Alright, Taylor. Come over here. We're going to put you in some funny costumes.
Taylor,
Just
come
sit.
Come on, Taylor.
Say funny things. Tell some jokes, why don't you?
Do you have any jokes?
I don't have any jokes.
Right,
Any math jokes? Math jokes are always the
I want
funniest.
to get back to I want to get to the
Oh, let me do this.
the bases.
I want to get to the faces. Here's the faces. See this?
See, no change.
That was not offensive in the slightest. It's a good thing we know Taylor, and he's a good sport about things like this. You give him a cowboy hat. Maybe Indiana Jones.
My name is John Wayne.
Seriously? Oh no, you're gonna unplug my... Oh, you shook it and everything. Now I have to...
Okay, now we're going to put Josh in some hats. He has the cowboy
Nope,
hat.
not that one.
Oh, now he has beer bottles over his head, but that was
Not
only
that
an
one.
accident.
That was totally
They were soda
accidental.
bottles.
I don't actually
Oh,
endorse
now
that.
we got... Hey, there we go.
There we go.
Now,
Alright.
now he's amazing.
We are all done.
Josh,
That
inspirational words.
That is everything to do with polar coordinates. You are now a genius.
And, wait,
Oh.
if your school has it, join Calculus BC. It's the bomb.
Oh, there's Chase.
There's Chase. He's also in our group.
Alright, sweet. I think I just hit stop.